All right, moving forward here to number 7. We have we didn't really talk about it at the time, but back in section 3.5, we have a picture of what 1 over x looks like. It looks like this right here. It looks kind of like not. It's definitely not a parabola, but it kind of has that look to it. It looks like some of the things we graphed in 3.5 when we had the vertical asymptotes and everything. And as it turns out, just to give you a brief description here, when it's 1 over x, and that's all that it is, the vertical asymptote is the y-axis, and the horizontal asymptote is the x-axis. And so that's why it ends up looking like this. And so let me go ahead and graph that right now here on this graph. Just as a reference point, we know that when I plug in x equal to 1 right here, I'm going to get 1 over 1 equal to 1. So that means that when x is equal to 1, y is equal to 1. And then if I plug in x equal to -1, again, just so you can see where it's going here, if I plug in -1, I get 1 over -1 equal to -1. So that means that just to have some points to go off of here, these are a couple of points on this graph right here. Just to have something to kind of point our graphs from. So it ends up looking like this as that picture just described that I showed you from section 3.5. Okay, so let me draw that. And then we'll, again, the vertical and horizontal asymptotes are the axes that you see there, x-axis and y-axis. Is this 1-to-1? Yes, it is, because it passes the horizontal line test. Okay. Let me write that down. Passes the horizontal line test. It is 1-to-1. Okay. And so step 2 then means what? It means that we keep going now and we figure out what the inverse is. So I change the f of x to y. Okay, and then I interchange the x and the y like we've been talking about. And as we've seen a number of times, especially in that same section 3.5, when you have a fraction on one side and just a term on the other, you can make this into a fraction also so that you can cross multiply. And that's important here because we ultimately want to now get y by itself. If I cross multiply, I get x times y equal to 1 times 1, which is 1. I then can then divide out by the x here to get the y by itself, because I had just a single term on one side, a single term on the other, single term with the variable, single term without it, and it was y to the first power. So it's just like a typical linear equation, all right, where you've got just a regular monomial term on each side with y to the first power, y being the variable that we're trying to solve for here. So we would divide out by the thing that's being multiplied by y. No different than if you had like 4y equal to 1 or 6y equal to 1. You would divide by that thing that's being multiplied by the y. So we get 1 over x, but how interesting is that though? Okay, it's actually the same exact function that we started with, all right? This is rare, but it could happen sometimes that the original function you start with is actually the same as the inverse function, okay? And this is an interesting development here because if I were to graph it, it's going to be the same exact graph. So I don't need to do the dotted line like I normally do in the previous problems here. I don't need to draw that because I already know what the graph looks like. So no dotted line needed here in order to draw the inverse because I already know it's the same exact graph since it's the same exact function. So I'm just going to draw it right on top of it here. Kind of make it look like it's on the side actually so you can see it better. But it's meant to be right on top of it here. Okay. So the red graph and the penciled in graph there are both meant to be the same. Okay. And lastly here, what is the domain and the range of both f and f inverse? Starting out with the domain and range of f, all right, they are They are going to be, whenever you have a function like this where it goes forever to the left, forever to the right, that means it's always going to start at negative infinity, and it's always going to end at infinity over here. Notice I put a big gap in between. It's because it jumps at 0, doesn't it? Okay, we saw that a lot in section 3.5, where it goes forever to the left, and then as it moves from that arrow towards the right, if it keeps on going continuously without jumping until it gets to the vertical asymptote, then that means that there is a gap there at 0. And whenever, as we said back in those sections 3.5, when you have a vertical asymptote, that number where the vertical asymptote is, the x number there, since x is related to the domain, the x number there is not going to be in the domain when you have a vertical asymptote at that number. And so we need to say negative infinity up to 0, and then it's going to stop at 0, and then it's going to start back up again on the other side of 0, and that's why I did the little u right there, because we always have that u, right, when the graph jumps and starts back up again. And then it starts back up again on the other side of 0 because the graph approaches the vertical asymptote on the other side. So just like we saw in 3.5, if you have a vertical asymptote, it is going to jump. The domain is going to jump there, and it's going to still going to be still going to go up to 0 on both sides here. All right. So for example, let's say, for example, you had a vertical asymptote at 2. Then you would have 2 here and 2 here with the union in between. That's how it works with vertical asymptotes. I know we haven't talked about domain and range in relation to vertical asymptotes, but that's what happens, all right? You'll have that type of thing happen. And then once it starts back up again on the other side of x equal to 0 right here, it goes continuously forever to the right, thus indicated by that arrow going forever to the right. And so that's why there's no more breaks in the graph, all right? And so this is our domain then. So if you've got a graph that goes forever to the left, forever to the right, and then the only break, the only jump in the graph where it's not continuous is at a vertical asymptote, then wherever that vertical asymptote is, okay, is going to be the only break in the graph. So again, like let's say again that it was 2. Let's say it was at x equal to 2 instead of x equal to 0. Then you would put negative infinity 2 and then 2 infinity. Okay, it's that same idea. Speaking of asymptotes, when we do the range, you guys, the horizontal asymptote now affects that. Notice again that speaking of forever, this thing goes forever downward and it goes forever upward. So once again, it's going to start at negative infinity and it's going to end over here at infinity because forever down means negative infinity when you talk about the range. Forever up means that it's going to be positive infinity on the other end. Okay, so again, in a very similar manner, if you go forever down and then you go up all the way up until you get to this horizontal asymptote, and that's where the graph jumps, okay, and then the graph after that starts back up on the other side of the horizontal asymptote, right next to it, right above it, and then it goes forever upward after that. When that type of thing happens, then the range is very similar. It is also going to be like this right here, the same exact answer as the domain, because the only break in the graph was at 0. Okay, because it went all the way up to 0 on the bottom end of 0. I'm talking about y equal to 0 here, which is the x-axis. It goes all the way up to y equal to 0 right underneath it, and then above the x-axis, the graph goes all the way down towards it right above it. And so basically y equal to 0 is the only place where there's a break in the graph. Okay, so that's the domain and the range. And as you guys now know, the domain of f inverse is the same thing as the range of f. So I can just write that same thing down here again. Just give me a moment to do that. And then the the range of f inverse is going to be the same thing as the domain of f. And so I'll just bring that down here. And there's your answers for the domain and range. Okay, so that is number 7 right there. Again, don't be alarmed if your inverse ends up being exactly the same as the original function. That could happen sometimes, although it is rare. Going down here into number 8, x to the third minus 2, that stems off of back in section 2.7, we learned if you have a variable taken to the third power, it typically, and this is no exception right here, it typically will stem off of this graph right here, and then you could do those same things that we did back in chapter 2, where you can, and we won't even need to go that far here, but you can use the same x values, all right, as long as the thing that's being cubed is also x, and you can see that's true here. Okay, so if it was x minus 5 being cubed, for example, then you'd have to do this thing with the x minus 5s like we did there. But since it's just x being cubed, just the variable is, then you can use the same x values that we did back in section 2.7 right here. I know it says 2.6 right here, but that's where the basic graphs came from. And we learned that technique in 2.7. But we use those same 5 numbers right there for the x's. Okay, as long as the thing that's being cubed in your current problem is also x, once again, just like in the basic graph that I just showed you there. So that means we use those same 5 numbers, and then we just have to plug it into this current graph. All right. Again, if this had been like bracket x minus 5 being cubed, then that'd be different. Then you'd have to set all of these numbers equal to x minus 5. We talked about that in chapter 2, and we'll be talking about stuff like that, similar to that, coming up here in a couple sections, in the next couple of sections, in fact. You'll see that. We'll see that with some other basic graphs. But for now, let's plug in -2, -1, 0, 1, and 2 here. If I do that, I get -8. -8 minus 2 is -10. Plug it in like that. Exponents before subtraction. Sorry, I plugged in the wrong thing there. Hold on. -1 cubed minus 2 is going to be -3, and then you just keep on going on down the line here. 0 cubed minus 2 would be -2. 1 cubed minus 2 would be -1, and then 2 cubed minus 2 would be 6. Okay? And so we're going to go ahead and graph that now. Okay, so let's go ahead and graph this now. And so 2 comma 6, the 6 is a little bit above here, not too much, so that'll be fine right there. 1 comma -1 is all the way down here. Okay. 0, -2. -1, -3. And then -2, -10, I said you didn't have to graph it, but you could, all right, just by realizing that if I keep on going down here, -6, -7, -8, -9, -10, it does fit. We do have enough room. So I'll go ahead and put that down here. All right. And so following that same basic shape from chapter 2.6, the graph is going to look like this right here. Okay. Now, anytime we graph that original function, the first thing we ask is it 1-to-1 based on what you see there? Well, you can clearly see there that the graph passes what? What does it need to pass in order to be 1-to-1? It needs to pass the horizontal line test, right? It does. And so, therefore, F is 1-to-1, isn't it? So what's step 2 then? Since we know it's 1-to-1, we need to do the rest of the problem. Okay, what is this next step here? We need to then figure out the function formula for F inverse. So change the f of x to y. that. And then what do we always do after that? We interchange the x and the y, so the y becomes an x and the x becomes a y, like that. And now we need to solve for y, the new y that we have. Okay. Now this is similar to something that we've done before when you have y to the third, all right, and you need to get y by itself. Back here in section 1.4, we learned how to solve for x when x was taken to the second power and there was no other variable in the equation. It's the same idea here where we need to solve for y when y is taken to a power and there's no other y in the equation. Okay, it's a similar thing. Let's go through that. The first thing you do, just like I did here, is you move the other terms over to the other side so that the x squared was by itself. In the same way, I need to move the 2 over with the x so that the y to the third is by itself. All right? So just like you want to get the variable squared by itself, okay, and then do that radical thing here, it's the same idea with y to the third. You want to get that by itself. The way we get that by itself, assuming there's no parentheses to clear out first, is to move over the 2 by adding or subtracting it over. In this case, you add it over because it's negative 2. So we get what? We get x plus 2 is equal to y to the third. Okay, and then that means what? That means that it's not exactly the same as it was here for x squared because it's cubed this time instead of squared. All right, here's how it works. Instead of doing the double square root, okay, because cube roots are different, we only need to do a single cube root, but it has to be a cube root. All right, but you only do one. You don't do the 2 different radicals like we did with the square roots. Okay, you just do a single cube root. So if you've got a variable to the third power, and that same variable is not on the other side, it can't be over there, okay, otherwise you can't do this. But if you've got a variable to the third power, and that same variable y in this case is not over here, you can go from y to the third to y by itself by taking the cube root of the other side, but just a single cube root, not 2 radicals. Now that I've done that, now that I've got y by itself, I now have f inverse of x is equal to the cube root of x plus 2. Okay. And that is your function formula. Okay. Now that I have my function formula, I need to do my graph. And again, it's up to you. Like I said before, do you want to graph this? Or do you want to just use the dotted line and to reflect it? I'm going to go ahead and use the dotted line and reflect this. We could graph this using the 2.7 techniques because we did have a cube root of x basic graph from that section and from 2.6 where those basic graphs came from. But since we didn't do that very much, we didn't have much experience with that, yeah, we could still do it, but it'd probably be easier just to do the reflection here. Let's see. Let's do that. Okay. So here's what we get. Like that. So if I reflect it over that, what does that mean again? That means I turn my paper, okay, like that. And you take whatever's on the right-hand side of the line and you pretend like you're folding it over. Wherever it lands, that's where it ends up. You can plot these 4 points to help you. Here, let me go and do that. That one would be, that's 1, -1, so now it's going to be -1, 1, flipping those numbers around. This one is 0, -2, so now it's going to be -2, 0. This one is going to be -1, comma, -3, so now it's -3, comma, -1. And then this point right here was what? It was -2, comma, -10. So now it's going to be -10, comma, -2, way, way, way out here. Okay. And then remember, just as another way of helping you here, remember the shape is going to be basically the same. It's just going to be turned in a different direction. Remember also that the graph always intersects with its inverse right on the dotted line. So we know that there's another point right there as well. And so it ends up being something like this right here. Okay. Don't forget that arrow on there, because if it flipped over, all right, that arrow will go with it when it flips over. All right. How about this part right here? This part's a little bit easier. All right. If I take that part that's on the left side of the dotted line and I fold that over, where does it land? It lands like that, doesn't it? And so that's what the graph looks like right there. Okay, I know it looks like it's getting completely horizontal right here, but that is not what it's supposed to do. And I know that because if the original arrow, you guys, is not completely, let me turn it around. If the original arrow is not completely vertical, which it's not, it's close to vertical, but it's not, then when you do the inverse, it will not be completely horizontal. It's very, very close to being horizontal, but it's not. And that's really important because that means that the graph does go upward forever here. It just goes upward very, very, very slowly because it looks like it's almost horizontal, but it does go upward as it moves on out forever and ever and ever. Same thing here. This goes downward forever, even though it goes down very slowly because it's almost flat here. But because this thing is not meant to be completely vertical, this thing is not completely horizontal. And so what I'm trying to point out here is that the domain of this red graph, as it looks, is going forever upward and forever downward. That's for the range. We can clearly see the domain is forever to the left and forever to the right, but it does go forever down and forever up. Okay, since it does all four of those things, we would expect that the red graph would have a domain and range that's equal to everything from negative infinity to infinity. But let's make sure, remember, it has to agree with the domain and range of the original graph. All right, so since the domain and the range of the original graph, they are equal to, because this goes forever to the left, even though it looks almost vertical, it does do that. It's just going to the left very slowly. All right. That's just how the x to the third graphs look, you guys, by the way. That's how I know that. The x to the third basic graphs that we learned in 2.6, they always go forever to the left and forever to the right. There's no doubt about that. All right. Irregardless of how they look. And so the domain and range of the x to the third graph, and therefore this as well, since it's basically the same shape, is going to be negative infinity to infinity on both the domain and the range. So that means that the domain and range of the inverse graphs, or the inverse graph, must also be the same, because as you know, the domain of the original has to equal the range of the inverse, and the range of the original has to equal the domain of the inverse. Okay? And so that now proves, because these two things are both negative infinity to infinity, that this is got to be the correct graph, and we don't need to adjust it to match this domain and range, because this domain and range does match what we have here in red. Okay. In this next problem here, we will need to make an adjustment with the final red graph here. Again, that's why I keep on saying make sure that the red graph matches up with the domain and range that comes from the domain and range of the original function. Okay, it has to match that. We'll see that it doesn't match that in the next problem, so I'll show you how to deal with that. Okay, but we do need to keep that in mind here on each problem here, because you never know when that situation could arise where you got to adjust the red graph according to the domain and range of the inverse that we need it to be equal to, stemming off of these two here. Okay. All right, number 9, last one here. Step 1. Let's graph to find out if it's 1-to-1. Because we're square rooting something in the function with a variable in it, that means that it stems off of this original basic graph from 2.6. But since and anytime you have something that's square rooted in one of these graphs, you take the thing that's being square rooted, and that's the thing that you set equal to these 4 original numbers. All right, just to give you a visual there, you can see that we had that here with x plus 1. Since we were square rooting x plus 1, we'd write down x plus 1 and set it equal to those 4 original numbers. We solve to get these 4 new x numbers, and then those are the numbers we plug in to get the new y numbers. And these are the 4 points that I plotted. It's the same exact thing right now. Okay, we take x minus 2 because that's what's being square rooted, and we write down x minus 2 4 times, set it equal to those 4 original numbers for the square root of x function, 0, 1, 4, and 9. Okay, and what does that make x equal to here? If you add the 2 over to the other side to get x by itself, it is going to be x equal to 2, x equal to 3, x equal to 6, and finally x equal to 11. You then take those 4 numbers there, you plug them into this function to figure out what the new y values are going to be. And just remember that you need to plug in. After you plug in, remember you got to figure out the inside of the radical before you take the square root. So plugging in 2, you get square root of 0, which is 0. Plugging in 3, you get square root of 1, which is 1. Plugging in 6, you get square root of 4, which is 2. And finally, plugging in 11, you get square root of 9, which is 3. So these are the points you want to plot here. Again, 11 is a little bit off the board there, but again, if it's just 1 point that's off the board, all right, that's usually okay. You can plot these other 3 as long as you use the correct shape right here. And we know that the basic shape for a square root of x is this one here, where like it's got an arrow on one end and it stops on another end. All right. How do I know where it stops? It always stops at the same point where let me go back here. See how here x was equal to 0? So whenever you set the x minus 2 equal to 0, or whatever that thing was inside of the radical, whenever you set that equal to 0, whatever that answer is where it stops. So if this had been like x minus 5 here, x minus 5 equal to 0, you solve that, which would be x equal to 5, then it would stop at 5. All right, so it's just wherever, whatever new x value you got that came from the old x value of 0, that's where it stops. So we know that the graph stops there, and let me plot the other points here. 3, 1. 6, 2 is over here. 6 is right there. And then 11, I'll just go ahead and plot that. It's way out here. 7, 8, 9, 10, 11. I'm just saying that you don't necessarily have to if there's not room, but we can here. And that leads to what here? That leads to this graph right here, like that. Okay. And so that's the original graph. Again, I know it looks like it gets almost horizontal here, but it doesn't. That's just not the nature of this graph here. It goes up. It still continues to go upward forever. It just goes up really slowly. That's all. But it doesn't get completely flat. And so it does pass the horizontal line test, all right, because this thing's going to keep on moving upward. It's not going to curl back around to where a horizontal line would hit it twice. That's not going to happen. So this will be a function, all right. It passes the horizontal line test. I'm sorry, what I meant to say was that it's going to be 1-to-1. Of course, it's a function, but because it passes the horizontal line test, the function is 1-to-1, and so we got to do the rest of the steps here. All right, what are those steps again? First thing is we figure out the function formula for the inverse. Change the f of x to y, just like always. Then we square both sides. Why do I square both sides? Oh, I'm sorry. I'm sorry, you guys. I got ahead of myself there. What do we always do after we change the f of x to y, if necessary? What we do after that is we take the y, and that becomes a x, and we take the x, and that becomes a y. Okay, now we need to square both sides, and the reason why is because anytime you've got a radical equation, we talked about this in chapter 1, anytime you got a radical equation with a variable stuck inside of that radical, you have to square both sides there in order to get that variable out of the radical, and then you can solve. It's not going to be this long, but that's the idea, though. Since the variable that I want to get by itself is stuck inside the radical right there, the y, I need to square both sides. The radical has to be by itself, but it is. And we get x squared is equal to y minus 2. When I want to get again, what we have here again is if you've just got a polynomial on both sides with no parentheses, and you want to get a variable by itself, you take the terms that have the variable in it. Those are the red ones. The terms that don't have the variable in it, those are the green ones here. Assuming that the variable is to the first power, by the way. If it's to the second power, then you don't necessarily do this. As we saw in that last problem here, we need to do something different. But if it's to the first power, then you do this thing where you move the terms that don't have the variable in it. Okay, the variable you're trying to solve for anyway. You move those over by adding or subtracting them over so that the term that has a variable in it will be by itself, and then you divide out if you need to. Like if this was 3y, you'd have to divide by 3, right? But since the y is already by itself, that means that we now know what the inverse function is. It's equal to y, which is equal to x squared plus 2. All right, now, normally, you guys, when you do x squared plus 2, all right, that's going to be a full-blown parabola. All right, but that's not going to happen here, as you'll see. Okay, let me show you why. If you do graph this, remember I said you could graph either do your inverse graph either off of the formula, which means that we would base it off of our 2.7 method, where you realize that this is going to be, because it's got x squared in it, it's going to be a parabola, and then you do all the steps there to do x squared plus 2, all right, and you'll end up with this parabola, all right. But I'm not going to do it that way because I already know that I'm going to have to adjust that, as I promised you in this problem. And again, if you graph that full-blown parabola, you can always change it. Okay, you can always fix it after that, so don't worry about that. But I'm going to show you here that it's not going to be a full-blown parabola, not just because I'm doing the reflection here, but there's another reason as well. Okay. I'm going to do the reflection here, and you'll see that it's not a full-blown parabola. Okay, let's see. There we go. Okay. So, as you can see, the entire graph is, as I spin this around, the entire graph is on the right-hand side of that dotted line. And so you just need to do one reflection. There's nothing over on the left that you got to fold over to the right. It's just from the right, fold it over to the left. Okay? Use your points that you've already plotted to help you. 2, 0 becomes 0, 2. 3, 1 becomes 1, 3. Okay. 6, 2 becomes 2, 6. It's about right there. And then that one's just going to be way up there. All right. I'll just go and put it up there. And then folding this thing over now, where would it land? It would land right here. Don't forget to put the arrow on there. In fact, I'll go ahead and make that arrow go a little bit further, all right, to make it match up with that. But that's what happens there when you fold that over, right? But look at what I just did, though. I've only got half of a parabola. If I were to graph this thing right here, it would be a full-blown parabola. Okay, so what went wrong here? Did something go wrong? Now, this is what I was talking about when I said that your domain and range of the original function have to match the domain and range of the inverse. Okay, let me write down all four of these things here again. All right, again, the domain of the original graph has to match the range of the inverse graph, and the range of the original graph has to match the domain of the new graph. What is the domain and range of the original graph of f? Not f inverse, but of f. You can see here that the graph starts at 2 on the left and it goes to infinity on the right. So the domain is going to be, and this is a continuous graph, so you can do your domain and range in the normal way here. Okay, it's not like up here where we had a break in the graph, and so you got to kind of go about it a little bit differently. You can just do it in the same way we did back in 2.3, where you look for the leftmost point and the rightmost point, the lowest point and the highest point for the range, all that stuff that we did. We get 2, infinity for the domain, 2 on the left, infinity on the right. For the range, we go low to high. The low is at y equal to 0. And since this does go upward forever, even though it goes up really slowly, the highest point is infinity for the range. So that means that these two things down here need to be the same. This one has to be 2 to infinity, and this one needs to be 0 to infinity. So if I had graphed the full-blown parabola, taking it off of this formula here, it wouldn't have matched these two things right here that I'm pointing at, the domain and range of the inverse. But this graph does. Okay? That's what's important here, is making sure that whichever way you do, whether you do it the inverse graph off of the formula or if you do it off of the reflection, make sure that whatever you end up getting matches the domain and range of the inverse. All right, you can see now that this is the leftmost point is 0, going forever to the right. So the left is 0, the right is infinity, and that's what domain is. It's from left to right. So it matches up with this parabola. If I had done the full parabola, it would have had to have been negative infinity to infinity. But no, it's supposed to be the same as this one up here. It has to be. So this is the guideline you go by, is this range has to be the same as that, not the same as whatever the function formula gives you. It has to be the same as this. And similarly, the range of the inverse has to be the same as this, not the same as whatever the formula is telling you. Okay, so this is the correct graph. Now, one more thing though. When this happens, you guys, you have to make an adjustment on your formula, because this formula is implying that we have a full-blown parabola here. So what I do, kind of like what I did with piecewise functions, you just need to put a little note here next to this with a semicolon, and you want to indicate that this is not a full-blown parabola, but it is just the part of the parabola where x is 0 and then to the right. It starts at x equal to 0 and then it goes to the right. What does that mean when you start out at x equal to 0 and you go to the right? It means that x is greater than or equal to 0. Okay? So I need to what? I need to, let me just make a note down here. You need to make additional condition. That's the word I was looking for. Sorry about that. Make additional condition. When you put that x greater than or equal to 0, that's just an additional condition that says that, hey, this is not the normal graph that you normally get. But by putting this condition on here, just like with piecewise functions, it's just a part of that graph based on the condition that's off to the right here. Okay, so you make that a conditional, and that you make that additional condition to make f inverse of x, that formula, to make it match match up with the domain and range of F inverse. It has to do that, as we talked about. Okay, what domain and range am I talking about? I'm talking about this right here. Okay, it has to match up with that. And so make that adjustment. Okay. So if for example, if the domain had said -2 to infinity, then you would say x greater than or equal to -2. Because if it's from -2 to infinity, that means that x is anything that's bigger than -2. All right. You don't need to write down any kind of additional condition for the y value. So you just have to do the x's and you'll be fine. Okay. So again, if this was -5 to infinity, then you would say x greater than or equal to -5. That's how it works. Okay, so you just need to make that additional condition if unlike the other problems that we did where the domain and range matched up to the graph that we got, if it doesn't match up, okay, if the graph doesn't match up to the domain and range, which these are definitely right because they have to come from here. If the graph doesn't match up, you then have to fix the graph. And then once you've fixed the graph, all right, and it's fixed now because it starts at 0 like this says it's supposed to, then you put that condition on the inverse formula. Okay. But as far as the function formula is concerned, the reason why I knew I had to put the condition on there is, in other words, why did I not have to put conditions on the other problems where I had the function, the F inverse formula? It's because once I do my graph right there and I fix it, like if I had done the full-blown parabola first, this would have told me to just get rid of everything except for from 0 to infinity. So I would have gotten rid of part of the parabola there so that it just goes from x equal to 0 to x equal to infinity. Once you do that, okay, no matter how you got the graph, once you do that to get it to match up to that, then you say to yourself, okay, wait a second, I know that this this is not just half of a parabola. I know that this is a full-blown parabola because it's similar to those 2.7 problems. That's when you know you got to put that condition on there. Okay. It can never hurt to just put that additional condition on all of these problems here if the domain is less than all real numbers. If it's all real numbers, then you never need the condition, okay, for the F inverse and the x's here, because see here, this is everything. Okay. Like for example, up here, you could, not that you have to, all right, because it's already implied when you look at the fact that the domain can't have 0 in it since it has since the denominator can't be 0. But you could say, after you say 1 over x, you could write down x is not equal to 0 right here, which is the same thing as saying that the domain is equal to this, and so it would match up. It's just that it's already known, all right? So you didn't have to, but you could say x not equal to 0 right here if you wanted to as an additional condition next to that. It doesn't hurt to do that because that is the correct domain. So you're being a little bit redundant there since we can already tell that the x can't be 0, but it wouldn't be wrong to do that. Okay, if you want to be sure. So you can always put that condition on there based on what the domain of the inverse is. All right. So if the domain is missing a number and everything else is there, how you say that is x not equal to that number. And that implies that every other number is in the domain. These other two problems, like I said, the domain is already everything, so you don't want to put any condition on the domain of the inverse when the domain already includes every number in the world. Okay. But in reality, this is the only one you really needed to do it on because this formula already, you look at it and it looks like a full-blown parabola because it comes from 2.7 when we had the full-blown parabolas. So we needed to put that condition on there. All right, to make sure that it is consistent. This formula is consistent with the red graph. All right, this is half of a parabola, but without this condition here, it looks like a full parabola. All right, we want it to be the same. It needs to be the same. Okay, so that's why we need that condition here. It's kind of a weird thing, so I just wanted to, pardon me if I'm being a little bit overly wordy here, but I wanted to make sure that you understand why that has to be there. Okay, it's when the graph, all right, it's when the graph does not match up with what the formula would normally give you, which in this case is a full parabola. All right, that's when you got to put that condition on there. All right, and we know that that's what the graph is because it is it's got to match up with that domain there. All right, so that is section 4.1 on inverses. All right, let me know if you have any questions. As usual, you have a good day and take care.